Today we're going to be talking about solving systems of linear equations. A system of equations is any time you have at least two equations where you're looking for solutions that work with both equations. If it's a system of linear equations specifically, both equations will be linear and both of them will use the same variables. So for example, if you had the system of equations x plus y is 0 and x minus y is 2, then that would have the very, very unique solution that the only set of numbers that this is possibly going to work for is the point 1 comma negative 1. Since if you were to plug that in, 1 plus negative 1 does equal 0, and I should have actually plugged in 1 for x there instead of just rewriting x, and then 1 minus negative 1 does indeed equal 2. Now typically you don't want to just guess and check until you find all the points to satisfy the system. So it's good to have kind of a visual of what's going on, and visually solving it is a very, very valid strategy that is, in my opinion, the most intuitive. So if you're going to solve them visually, that would be solving by graphing. And in particular, what you would want to do is rewrite both equations so that they are in slope-intercept form. So that's y equals mx plus b. That's probably the nicest form to look at any given set of linear equations in. Graph them both on the same coordinate plane, and then you're going to want to interpret the intersection. There's only physically three possible ways this intersection can work. Either you have what's called an independent system, so they are two completely different equations that intersect at exactly one point. That one point might be a little bit messy, might be a fraction, but they'll intersect exactly one place. The fancy word for that is being consistent and independent. Theoretically, what you can also have is a situation where you have no solution. So if you have a set of parallel lines, that means that they have the same slope but different points, and they will literally never touch because they have that same slope. So that would be called inconsistent if you're using fancier language for it, aka no solution. A dependent system is going to happen when in some way I give you the same equation twice. So if I gave you x plus y is 2 and 2x plus 4y is 4. Oh wait, sorry. 2x plus 2y is 4. All I did was multiply each of those variables and constants by 2, and this is literally the exact same equation. If I were to solve for y in both of these instances, it would work out to the exact same equation because that would, for the first equation, subtract x on both sides. That's y is negative x plus 2. For the second equation, start with subtracting 2x on both sides, then divide by 2, and you still get y equals negative x plus 2. So when I somehow give you the same equation twice, that will be known as a dependent system, aka infinitely many solutions. Oftentimes you'll want to talk about how there's infinitely many solutions, so you'll want to write down what the equation is. So the key thing is to make sure that you are actually finding the for real intersection. You're not just guesstimating what it is, and making sure you're very careful about graphing correctly. As long as you do that, you should be good to go solving by graphing. So I'm going to go ahead and encourage you to pause your video and solve these two equations yourself before we go over the solution. So for this first one, this is a independent, consistent system with a single solution at negative 1 comma 1, because that is the point where they intersect. For the second one, it looks physically like these are likely parallel, but it's worth actually confirming. So what I would do is pick two clear points on your graph. So in this case, it looks like it's going up 3 over 1, so this has a slope of 3. By 3, I mean in terms of how the plot is actually labeled. And then for this next one, again, I want to pick two very clear points on the graph where it again looks like it's going up 3 over 1, so it has a slope of 3. So as long as you confirm that their slopes are the same, you're good to go, and you can say this is no solution, aka these are inconsistent. Inconsistent, independent. being the fancier way of saying no solution, as you saw up here. Oftentimes you won't be given the graphs though, you'll typically have to create the graph yourself. So go ahead and pause your video and try to find the solution by graphing for both of these problems. So for the first one, both of these are already in slope-intercept form. So for the first equation, I'm going to start at positive 4 as its y-intercept, and then move according to its slope. So that would be down 2, right 1, down 2, right 1, down 2, right 1, down 2, right 1. As you notice, I'm actually trying to very carefully map out as many clear points as I can, because if I'm going to be finding where these cross, I want to be as precise as possible. Then for the second equation, do a similar process. So its y-intercept is at -1, and then its slope is positive 3. So that means going up 3, right 1, or alternatively down 3, left 1. Either way, I did, through that process, just discover the exact point where they cross, which in this case is at the point 1, 2. Now, I can check my work by actually just plugging it back into the equation. So it should be true that if I were to plug this point into both equations, the equations will be true. So if I plug them into the first equation, plug in 2 is y, -2 times 1 is x plus 4. -2 times 1 is -2. -2 plus 4 does indeed give me 2. I'm good. And then if I plug them into the second equation, that would be 2 is equal to 3 times 1 minus 1. 2 is equal to 3 minus 1, since 3 times 1 is 3, which leaves me with 2 equals 2. And I am good to go because that is indeed a true statement. For the next example, where one of these is already set up and ready to go to plot. So for y equals -1/2 x plus 2, that means we're going to start at a y-intercept of positive 2, and then move up 1, left 2, or alternatively down 1, right 2, and then continue the pattern in both directions. Then we're going to go ahead and draw our nice beautiful line through it. For the second equation, we've got to do a little bit of solving first. So in particular, I'm going to subtract 2x to both sides. 4y is equal to -2x plus 8. Then I need to divide all three terms by 4 to undo multiplying by 4. -2 over 4, both of those are divisible by 2, and it simplifies to -1/2. 8 divided by 4 simplifies to plus 2. And then this is a case where you notice, oh my gosh, these are the exact same equations, so they would be plotted right on top of each other. So in this case, this is considered no solution. It is a dependent system. So we're in that last scenario up here. So the system is dependent because really I just gave you the same equation twice. And just as a quick overview again, remember there are 3 different solutions that you can get whenever you have a system of 2 equations with 2 unknowns. Either they are 2 different equations with 2 different slopes, so they're going to physically cross at one point, or they are the 2 different equations with the same slope, so they've got different points with the same slope. That means they're parallel lines, and those would be considered inconsistent, aka no solution. Or they're really just rewriting the same equation twice, so that's the dependent system where it's infinitely many solutions because it's really just the same line.